When you're integrating powers of sines and cosines, I've got a motto for you to remember. You can trade sines for cosines or vice versa. How so? Well, since sine squared plus cosine squared is 1, right, that's the Pythagorean identity, I can use this to get these two facts, that I can replace sine squared x by 1 minus cosine squared, and can I replace a cosine squared by a 1 minus sine squared. This is often useful. Let's try making some trades. For example, let's try to antidifferentiate, say, sine cubed of x times cosine squared of x dx. Our first inclination might be to try to make a substitution. But rats, I mean, if u were sine x, right, then du would be cosine x dx, but I've got a cosine squared term there that I have to deal with. If I made a different substitution, like, u equals cosine x, well then du would be minus sine x dx, but then I've got a sine cubed term to deal with. So instead, I'll trade a pair of sines for a pair of cosines. So instead of making a substitution immediately, I'm going to trade a pair of sines for a pair of cosines. What I mean is that I'm going to rewrite the integrand as sine of x times sine squared of x times cosine squared of x. And then I'm going to use the fact that sine squared is what? Well, it's 1 minus cosine squared x. All right, so I can rewrite the integral as this. Now I can make the substitution u equals cosine x. So u is cosine x, and in that case du is minus sine x dx, which I don't quite see here, but I can manufacture that by including a minus sign there. So this becomes the integral of 1 minus u squared times u squared, and then minus du. Now I expand. So this is negative the integral of u squared minus u to the 4th du. Now I'll integrate. So this is minus, antiderivative of u squared is u cubed over 3, and an antiderivative of u to the 4th is u to the 5th over 5 plus c. Now I'll substitute cosine x for u. And we get negative cosine cubed of x over 3 plus, it's the negative of the subtraction, cosine to the 5th x over 5 plus c. And this same kind of trick works in other cases too. For example, what if I wanted to antidifferentiate sine to the 5th power times cosine to the 5th power? Since I've got an odd number of cosines, I can trade all but one of them for sines. What I mean is I can rewrite this integral as sine to the 5th times cosine squared times cosine of x dx. Right? This is 4 cosines times another cosine gives me cosine to the 5th. But now I can use the fact that cosine squared is 1 minus sine squared. So I can rewrite cosine squared squared as 1 minus sine squared squared, and then times cosine dx. And now we can finish by making a substitution. So I'll make the substitution, u equals sine x. In that case, du is cosine x dx. So the integral becomes, instead of sine to the 5th, it's u to the 5th. 1 minus sine squared is 1 minus u squared, and that's squared. And cosine x dx is du. Is that going to work? Yeah, I could definitely finish this off. I just expand this out, and then I get a polynomial in u, and I can antidifferentiate a polynomial in u, and then just replace u by sine of x to get the antiderivative of sine to the 5th cosine to the 5th. So what's the general pattern to this kind of trick? The trick works as long as I've got an odd power on the sine or an odd power on the cosine. Because in that case, I can split off all but one of them, and then I'll get, say, sine times an even power of sine times some number of cosines, or sine times an even number of cosines times cosine. And then since this is an even number here, I can rewrite those in terms of the other. So then I'll end up with a single sine times a bunch of cosines, really a polynomial in cosine x, or a polynomial in sine x times cosine, and then I can finish it off with a single substitution.